Good afternoon, students. How are you all? Good afternoon, Nitin. How are you? So, hello, students. So, I am Mukesh Mishra, your chemistry faculty at Aakash. Okay, and today I am going to discuss the various questions that were asked in mock test 3, which was conducted on 2nd Feb 2025, and all you must have attempted these questions. Good afternoon, Arushi. Okay, so in this session I am going to discuss the questions that were basically asked in for a GOC part, hydrocarbon part, and haloarenes and haloalkanes part. Okay, good afternoon, Debesh. Good afternoon, Nids. So I hope you must have gone through the papers and you must be ready with the doubts which you have. Okay, so let's begin with the session. Now, let's talk about this question. This is a very important question. Okay, so the question says that compound which shows geometrical isomerism is. Okay, so in this question we have to learn about geometrical isomerism, and I know you all know that what are isomers. Isomers are basically the compounds which have same chemical formula but they have different properties. Okay, if you look into your NCERT, then it has been divided into structural isomerism and stereoisomerism. And in stereoisomerism, there is a part that is called geometrical isomerism. Okay, then optical isomerism is one more type, but here I am going to discuss only about the geometrical isomerism part. So be ready with your pen, pencil, notebook so that you can note down each and every concept which I am going to discuss, because now I will discuss mostly all the points that are necessary for the NEET point of view. Okay, is this clear to all? So yes, compounds which shows geometrical isomerism. So first of all, let's learn about geometrical isomerism. Now, okay, Devesh Kumar has answered, but let's discuss about geometrical isomerism. These are the compounds which have same molecular formula, okay, but they will only differ in their geometry. Okay, but why we have to understand this? Because you know, one type of compounds, the compound which is showing one type of geometrical isomerism will have different properties, okay, from the other isomer which it have. So let's talk about geometrical isomerism. So compounds with same molecular formula but different geometry is there. Now, how this geometry can be different? This we have to understand. Okay, let's have a look. So see, I will give you a very common example which I am going to discuss here. Let's talk about butene. Okay, so butene, simply you will write that, okay, this is CH3, CH, double bond, CH, CH3. Okay, but if you look at the structural part of it, then you will find that it has two types of structure. This C double bond C, which is present at the second position, is basically planar molecule. Okay, so because of this plane, you know, it is basically present at 120-degree angle. So this angle here, one CH3 is there and one hydrogen is there. So this carbon is sp2 hybridized and having the planar structure. So this type of structure is there. Now another carbon, this CH3. Then we have H. Okay. Now have a look here. The second structure that is possible for this compound is C double bond C, CH3, then CH3 here, then it is H, and again one more H is here. So now you can understand that these two, even though they have same formula, but they have different structures. Okay. Now have a look here. One thing we have to understand that these two isomers have certain different properties. Okay. CH3 has electron donating effect. Okay. It has plus I effect. It will donate electron, and due to this, there is net dipole moment is there. Okay, mu is there because both the dipole moment are not cancelling each other. That's why it has net dipole moment. But Muhammad Shad, what will happen here? In case of C double bond C, CH3, you can see this type of electron donation is there, and they both, if you have a little idea about the vector, because dipole moment, you must have learned that it is a vector quantity, and if they are acting at 120 degree, 180 degree and with same force and in opposing direction, then they will nullify each other, and here the mu becomes 0. Okay. So this dipole moment is one of the property in which these two compounds are different. Another property is that because of this dipole moment, dipole-dipole attraction decreases. Therefore, boiling point of this alkene, this portion, is less. Okay. So you can say this is trans, and this one is, because it is on the same side, so we call it as cis. Okay. So cis has higher boiling point as compared to the trans because of this dipole attraction. And this is the exact reason why we have to understand the geometrical isomers. Now you must be aware of a fact that in alkane also you have learnt about the eclipsed conformation, staggered conformation. So can we call them as geometrical isomers? This is a very important question which you have to understand. Now try to understand here. Listen carefully. During conformation, what happens is that rotation around carbon-carbon double bond takes place. Because carbon-carbon double, the single bond is there, they both are held together by sigma bond. And because of this rotation, one of the projection can be converted into, okay, one of the projection can be converted into another projection. Okay. But what will happen in this type of structures if they are geometrically different? Now, if you try to rotate, see, we have to rotate through this C double bond C, and if we try to rotate, what will happen? This carbon-carbon double bond will break, definitely break. And because of this breaking, what will happen? That molecule will cease to exist. So that is not possible. In geometrical isomers, there is restricted rotation. Note down this concept that in geometrical isomerism, restricted rotation is there. Okay. But in case of conformation, there is no restricted rotation was there. Okay. So that's why conformers are different thing. They are not geometrical isomers. But here, and one more thing, that you can easily separate these two compounds based on their physical property. I can see in the comment section, someone has written that trans will have more melting point. Yes, this is also true because it has symmetrical structure, and because of this symmetrical structure, the trans butene has higher melting point. Okay. So now, one thing we have understood from this discussion, that restricted rotation must be there. What are the other factors which will decide? So, and another factor is geometry of molecule should be different. How does the geometry becomes different? You can see here. See, if I talk about the distance between CH3 and CH3 in this molecule, what is happening? They have a certain distance x. Again, this H and H are present at different places. So there is, let us suppose this distance is also x. Okay. Now, but in this compound, the distance between one CS3 and one CS3 has definitely increased. It is different from here. So geometrical arrangement, the geometrical parameters of these two compounds are different. Will trans have higher melting point or higher boiling point? Trans have higher melting point. The reason for this is because of more symmetrical structure in solid state, the fitting is there. Okay, so perfect fitting is there. So trans has more higher melting point. Okay, electricity. चलो नाम चेंज करके आओ, नया नाम होना चाहिए, पता चलना चाहिए कि किसका क्या नाम है क्लास में. ठीक है. Okay. So geometry should be different. And one more thing, that suppose we have certain compounds, C double bond C, Cl, Cl, H and H. Okay. So this will show geometrical isomer because carbon which is having the two Cl and H, they are completely different. Okay. But if the molecule is written like this, okay, tell me one thing, will this compound show geometrical isomers? In the comment box, I want to know that whether this compound will show geometrical isomer or not. This is because, again, the concept of geometry is there. Even if you exchange these two, the distance from the different distance from H and Cl and H and H will remain the same. There will be no effect on this. So the carbon which contains different groups, this is another criteria for being cis-trans or for showing the geometrical isomers. Okay. So this is one more criteria. Now restricted rotation. See, it is possible in various types of compounds, but from NEET point of view, you have to understand that you have to take care of basically alkenes and cyclic compounds, because even if cycloalkane is there, if cyclic structure is there, there is restricted rotation. Restricted rotation is possible in case of double bond alkenes as well as cyclic compounds. Suppose a cyclic compound is there and if you try to rotate it, what will happen? The cycle will break. At one point of time, you have to break the carbon-carbon bond. Therefore, we are going to discuss basically about alkenes and cycloalkanes. Okay. There are various types of compounds also which will show geometrical isomerism. Okay. Yes. Yes, because of the same group, they are not going to show, this one is not going to show the geometrical isomer. Good. Okay. Now, let's try to understand the case of various alkenes and cycloalkane. One very important question is there. Suppose we have a cyclic this compound is there. Will this show geometrical isomer? Will it form geometrical isomer? Yes or no? You have to understand this. So definitely a cyclic group is there, and because of this cyclic group, two substituent groups are there. Okay. So because of this cyclic nature, rotation will become restricted. Okay, Parnika? So everyone please note down this fact. Now how we have to visualize this? That is very important. A cyclic molecule is there. Now, what will happen? We know that this from this carbon, if CH3 is above the plane, here also if CH3 is above the plane, okay, and another type of structure that is possible is from here, it is one is below the plane and another is above the plane. Again, you can see these two are different from each other with their respective position. You can see the distance between CS3 and CS3 in these two have changed, have increased, means have changed. So that's why they are also geometrical isomers of each other. So this compound will definitely form geometrical isomerism. Now, if I ask you about this, will this compound show geometrical isomerism? Say yes or no. Will this alkene will show, oh sorry, not alkene, will this cycloalkane will show geometrical isomer or not? Okay, so you can see here that this will not form geometrical isomers, because if this one is above the plane and in another also, exactly not. If in another diagram it is below the plane, so they both are same. You just have to rotate it, okay, and you will receive the same type of molecules. Exactly. So because CS3 and hydrogen, even if they are there, but this is not going to show the geometrical isomerism at all. So this is how you have to find out. You have to find out the possible arrangement in which the geometry, the distance between the substituent groups changes, and that is the reason why a substance or a compound, an organic compound, shows geometrical isomers. Okay, so if you read your NCERT, then there is one very important statement there, that compound having XYC double bond WZ. Will this compound, see X and Y are different groups that are attached to carbon. Again, W and Z are also different groups that are attached to carbon, and they are different from each other also. I am giving you an example. C, Cl, F, double bond C, I, Br. Now, tell me one thing, will this compound show geometrical isomerism or not? So this is a very interesting question. Yes, please. You just have to see that whether any type of arrangement is possible that changes the dimensions, the distance between the geometry of the compound, the distance between two groups. If that is changing in different arrangement, then definitely it is going to show the geometrical isomerism. We may not call it as a cis-trans, but there is something which is also beyond NCERT. But this, at least this you must know, because in NCERT there is a line that compounds having XY, C double bond, C, W, Z, they show geometrical isomers. Okay? Yes. Okay, so now we will talk about this compound, that how many isomers are possible. Arushi has said that 3 geometrical isomers are possible. Okay, then please write in the comment box that how many geometrical isomers of this are possible. Yes. See, instead of learning about that, okay, if they are on same side, they are on different side, we have learned that if geometry is changing, then that is a different kind of isomers. So that is the basic reason for that. Now, how many geometrical isomers will be formed by this compound? Arushi is saying that, sir, 3 geometrical isomers are possible. Let's have a look. Now, how to draw the geometrical isomer of this? See, suppose we have C double bond C, F is there, Cl is there, Br is there, I is there. Now, I am not going to name that, okay, what kind of classification this is called, but you must know that how this shows geometrical isomer. Aditya Verma is saying that, sir, 4. Very good, well attempt, but let's have a look. Just make one group common, okay? Fluorine is common, okay? And here we have chlorine. Now, one more isomer that is possible for us is IBr. I have just inverted this. You can say that distance between fluorine and iodine here has changed, different distance between chlorine and iodine has changed, okay, and they can't be converted into each other. Okay, if you want to prepare these two compounds, you have to follow the different rules mechanism. Okay, so that's why they both are geometrical isomers of each other. Now, F, Br, then we have Cl, then we have I. If I just rotate these two, so rotation actually is not possible. So if I change this to, if I have a compound which is like this, so here you can see that we have another group. Again you can see that fluorine and bromine are common here, but distance between fluorine and iodine again and fluorine and chlorine has changed. Yes, Ez we call. So Parnika is saying 4. But let's bring iodine this side. I and Cl this side. Again, sorry, this thing is Br, and here also this is. So if you look at all these structures, even if they all have same molecular formula, but the structure, geometrical arrangement is completely different. So ultimately, this given compound FCl double bond ClBri, it will have total 6 geometrical isomers. So I think it was an interesting discussion. Sir, please draw the structure of COEN3 3+ for optical isomerism. So for optical isomerism, don't worry, optical isomerism in coordination compound will be taken by me. Okay, very soon. In that class we will discuss. Actually here I'm going discussing only about the organic compound. Okay. Is this clear to everyone? So one more thing you have to understand, that geometrical isomers, they are not the mirror images of each other. And as they are not mirror images, we call geometrical isomers as distereomers. Okay? So this thing is there. Now let's come back to our question. Compounds which show geometrical isomerism is. Now what will be the correct answer here? Any shortcut? No, there is no shortcut here, only practicing. By practicing, you will be able to find out that how many compounds, they actually, how the compounds will show the geometrical isomerism. This thing is by practice. Can we call this molecule as having geometrical isomers? Can you draw a certain image, a certain molecule which has different orientation, which has different arrangement? So this is not there, okay? This will not form geometrical isomer. If I talk about this second one, now try to understand this fact. We have already discussed, see, this type of arrangement is there if you can see here, if the molecule, both the CH3 are coming above the plane and in another one is above the plane and another is below the plane. In such case, you can see different arrangement is possible. Distance between CH3 here and CH3 here has changed. Yes or no? And this is the reason why this second will show the geometrical isomer. Okay. Let's talk about other options also. Here you can see we have cyclic group is there, and we know that cyclic compounds, they have ability to show geometrical isomers if rotation changes the one structure with 2 coming outward, 2 structure with 1 out, 1 in. Exactly. Or you can see that if you look at this cyclic structure in one plane, then one above the plane, another below the plane, or 2 on the same plane. Now some student might think that, sir, is it possible that if both these two are below the plane, will not be the third isomer, third geometrical isomer? So that is not the case. You just have to invert this and you will get the both the bonds will be in below the plane. So they are not isomers. Okay, so don't get confused here. Now here also you can see this compound is there, carbon H CH3. Again, no rotation is possible because two conjugated, two double systems are there. So here also this is not going to show any kind of geometrical isomerism. Yes, Arushi, it is same with the structure one. Now, if you look at this, C, CS3, CS3, double bond, C, CS3, H. Even if you exchange this H and CS3 in different structure, because this carbon has on same structures, what is going to happen? That their respective distance will remain same. So it will also not show the geometrical isomerism. So that's why this one is also wrong. So the correct answer is this second one. Is this clear to all? I hope I have discussed all the points which you have to keep in mind while solving the questions related to geometrical isomers. Now let's talk about number of geometrical isomers that are possible. Anyone having any doubt, feel free to ask in the comment box. See, if this compound is there, okay, tell me how many geometrical isomers are possible for this given structure. So in such scenario, you have to find out that if the double bonds are more than one, then you have to find out that on which double bond or on which part of alkene a geometrical isomer is possible. So here you can see on this alkene again, here hydrogen will be there, but two groups are different. So one structure is there, one double bond, okay, which can contribute in the geometrical isomerism is here. Then same is with this. Here also geometrical isomerism is possible. So generally the formula is 2 to the power n. Okay, number of centers that are responsible for geometrical isomers that you have to count. Then 2 centers are there. So the correct answer will be 4. So this is how find out. You can even find out that how many geometrical isomers will be formed for a given substance. Suppose if I increase one more carbon, okay, now, then it will become one more double bond is there, then it will become 2 to the power 3. But you have to be sure, you have to look at the structure always, that it should not be symmetrical. Okay, so you have to find out that whether the given double bond geometrical isomer is possible for that part of double bond or not. Okay. Is this clear to all? Now let's move on to the next question. So this was all about geometrical isomerism. Question number 59. So in the examination this was asked, in the sulfur estimation 0.2 gram of an organic compound gave 0.466 gram of barium sulfate, the percentage of sulfur in the compound is. So molecular mass of barium sulfate is given to you 233 U. Now how we have to proceed this? So first of all I will solve this question, then I will show you the trick or the imagination which you have to do to solve these questions. So see, in this compound we have a compound, and in Carius tube we put this for sulfur estimation, and then we add sodium peroxide is there, okay, and other nitric acid is added, so that H2SO4 is formed, and due to the formation of that H2SO4 ultimately barium sulfate is precipitated. Okay, so barium compound is again added. So finally the barium sulfate precipitation takes place, and now we have to use the stoichiometry. So Shrisha is saying that sir 32% is the correct answer. Now let's try to solve this. See, first of all you have to imagine, sometimes students they go for mugging up the formula, and there are slight chances that you might opt for the wrong formula during the examination. So let's try to solve this. We have taken a compound. Now, how much compound was there in Carius tube? Because this 0.2 gram. Okay, and then finally we precipitate barium sulfate. सर स्टडी एम्पायर सर अगर डबल बॉन्ड ना हो और कायरल हो तो बेटा मैंने बात की है सिर्फ अभी ज्योमेट्रिकल आइसोमेरिज्म की, ठीक है. डोंट वरी, I will be coming very soon with the classes of optical isomers. Again formula 2 to the power n ही होता है, but उसमें आपको optical isomers पूछे जाते हैं. Okay, don't worry about that. So now let's come to this question. Now here you can see that we have taken 0.2 gram of organic compound, and from this 0.2 gram we are getting barium sulfate. We are precipitating, taking out barium sulfate. How much? 0.466 gram. Means all the sulfur that was there in the compound has precipitated in the form of barium sulfate. Okay, so now try to understand that the 0.2 gram of the compound contains certain amount, let's suppose X amount of sulfur. So all that sulfur has been extracted out in the form of 0.466 gram barium sulfate. And if I find out that what is the amount of sulfur in barium sulfate, 0.566 gram sulfur, barium sulfate, then that is the actual amount of sulfur that was present in the respective compound which we have taken in Carius tube. So here you can see. Now simple unitary method, this you all have learnt in the stoichiometry, that one atom of sulfur is there in barium sulfate, and this one atom of sulfur, we can say that molar mass of barium sulfate is 233 gram. So 233 gram of barium sulfate has sulfur. How much? 32 gram. Is this clear to all of you? See how unitary method helps us in solving question like this. You have to note down. So 1 gram of barium sulfate has sulfur, that is equal to 32 by 233 gram. Simple unitary method. Yes. Now you can see that you actually obtained 0.466 gram of barium sulfate. So 0.466 gram of barium sulfate, this will contain sulfur equal to 32 by 233 multiplied by 0.466 gram. So this is the actual amount of sulfur that is present in barium sulfate, and this sulfur is the actual amount of sulfur that was present in our compound. So if we have to find out percentage, then we talk about the amount of that substance divided by total mass of the substance of the organic compound which we have taken. So if we have to find out percentage of sulfur, so mass of sulfur by mass of organic compound we have taken multiplied by 100. This is how we calculate percent. Yes or no? So what is going to happen here? 32 multiplied by 0.466 divided by 233 multiplied by, so total 0.2 gram is there, 0.2 gram organic compound we have taken multiplied by 100. Is this clear to all of you? And on solving this, what we are going to get? You can see calculation here is very easy. 233, 0.466, 0.2, just remove 1, 4.66, 100 multiply, it will become 466 divided by 233 into 2. So 233 cancels 466 by 2, 2 by 2 cancel out, and this comes out to be 32%. Is this clear to all of you? So the correct answer becomes option 2. So this method, generally we follow for the estimation of sulfur compounds. Okay, sulfur compounds. Then we also talk about here. So let's talk about halogen. How we can find out halogen. These are basically used for actually quantitative analysis of the compounds, halogen compounds is there. So this is actually done by Carius method. Okay. So Carius method, in Carius method what happens? That we take a Carius tube, okay. Very soon I will be taking about Geldal method and Dumma's method also, because today I am discussing about the Carius method. So don't worry, very soon I am going to discuss about Geldal and Dumma method also in the upcoming session. So be connected with me. I will take both of them simultaneously, most probably in next or next to next session. So you don't have to worry about that. So because these sulfur and halogen methods and phosphorus, they are of similar type. So we are dealing with that today. Okay. Now nitrogen estimation is different from these. So now have a look here. We are taking the organic compound. Suppose again, the organic compound contains a certain amount of organic compound we will take, and then we will add fuming nitric acid, and then we will add silver nitrate, okay. So that after the reaction, once in the Carius tube we put that, and when we heat that, we get AgX as precipitation. Yes or no? Now you will also ask that, sir, how we will know that whether this X is which halogen? So this Carius method is basically done to estimate quantitatively. In Lazine test, we have already discussed that how we have to find out the qualitative analysis is there. So for Lazine test, we do qualitative analysis where we can find out that which halogen is there. Now, if we have to find out the exact amount, then we follow the Carius method. Okay, and the Carius method again same. It has, suppose X gram of sulfur is X gram of any halogen is there. Okay, before performing this experiment, we already know that what is X in the given compound, whether it is bromine, iodine, chlorine. So that's why we will be using this method. So you can find out how. So molar mass of X divided by molar mass of AgX multiplied by, see, certain amount of AgX will be obtained, will be precipitated. So amount of AgX obtained multiplied by amount of organic compound which we have taken okay, and then multiply it by 100. You can derive it by simply assuming that what method I have used during the estimation for sulfur. Okay, so same method is there. By same method you can find out the molar mass of the amount of substance, amount of halogens that is present in the given compound. Is this clear to all of you? So they both have same method, same type of numerical. In fact, phosphorus also we obtain same thing. So this is how we have to follow this. Okay, now let's come back to the new question. So there is question number 60. Electrophile which is formed in the bromination of benzene in the presence of FeBr3 is. So we have Br plus, Br minus, Br free radical, FeBr2 plus. So please write in the comment box what will be your answer here. Basically, we all know that electrophiles are substances that are electron loving. So they will attack on the charge center where electron density is there, and themselves they are either electron deficient or they have positive charge. Is this clear? So FeBr3 is there, and you know what happens? Br is formed here, okay, bromine is there, okay, Arushi is saying Br plus, study empire, sir 1. Definitely. I've just told you that either it should have positive charge or electron deficiency must be there. Nidhi Vayugela, sir, option 1. Very good. See, very interesting questions I am going to ask. Okay. So yes, here what will happen? Fe Br4 minus is formed and Br plus is formed, which act as electrophile. So definitely answer will be this. Okay. Option 1 is correct answer there. And generation of electrophile is a very important concept for the electrophilic substitution reaction. Okay. If I ask you a simple question, I am allowing it to react with CH3, CH2, CH2, Cl. Okay. Once in presence of AlCl3 and once in presence of FeBr3. Will the product obtained be same or different? What's your answer here? Now, in this case, what happened during AlCl3? AlCl3 again, it will act as a Lewis acid. It will take the AlCl4. It will form AlCl4 minus, and then a carbocation will be produced here. These two are very important example which you have to remember. When we use AlCl3, Anushka is saying different, Rahul is saying different, then write the name of the compound that with AlCl3, this compound will be formed. With FeBr3, Y compound will be formed. You can write it very easily in comment section. So here what happens, when AlCl3 is used, a carbocation is produced once we are using CH3, CH2, CH2Cl. And this carbocation, undergoes rearrangement in order to increase its stability. Okay, because this is a primary carbocation, you all have studied that once primary carbocation is there, so primary carbocation will form secondary carbocation by hydride shift, and that propyl carbocation, what will happen? It will isopropyl carbocation that will react as a, yes Preeti, you are correct. So electrophile, and ultimately our product will be CH, CH3, CH3. Okay. Difference is that once we are using FeBr3, see this bond is not broken finally. Okay. So if we go into that much of detailed mechanism, then we find that free carbocation is not produced. Okay. One isopropyl benzene and second 2-bromo benzene. Okay. And here what will happen? So no rearrangement will take place, and here we will find CH2, CH2, CH3 as the product. Is this clear? Now, can any one of you tell that what is the electrophile generated during nitration of benzene? Yes. During nitration of benzene, what will be the product formed? What will be the electrophile that will be formed? Please be quick. Sujay is saying, sir, option 1. Where option 1 is? Yes. So during nitration of benzene, we have NO2 plus. that act as an electrophile. Exactly, very good. How it happens? We are using concentrated H2SO4 plus concentrated HNO3. This mixture is being used, and what happens here, that this H2SO4, OH, NO2 is there, it will release H plus. Okay, this H plus will form bond with this OH. It will ultimately form OH2 plus NO2, and once this is being formed, it will again lead to the formation of H2O plus NO2 plus. So this is how we get NO2 plus during the nitration, okay, and during the electrophilic substitution reactions of aromatic compound. Okay, then there is Friedel-Crafts acylation. Suppose we are using CH3, C double bond O Cl in AlCl3 anhydrous. What will be the product formed here? Sorry, not product, I am asking about the electrophile which will be generated here. So definitely electrophile silenium ion is there, that is CH3, C double bond O plus. This will be formed, okay. AlCl3 will take out this Cl minus, okay. And one more very important question which you all should know is that what will be the electrophile during sulfonation of benzene? Write in the comment box. Yes, during sulfonation of benzene, sulfonation. So these are various kind of exam questions which can be asked anytime. So you must be aware of the mechanism for the electrophilic substitution reaction. This mechanism I have already discussed in my previous lecture. You can even go back to the playlist where you will find GOC Kataz, organic paras. There also Pankaj Sharma sir has mentioned it. Okay, so if you watch that series, definitely it will help you. Okay, it's not actually the SO3H or HSO4 minus, basically the electrophile that is generated is SO3. Okay, SO3 is there, so that you have to remember. Is this clear to all of you? Now let's come to the new question. Which of the following is a temporary effect? H2SO4 is used as reagent. H2SO4 react as with another molecule of H2SO4 and it generate H2O, SO3, HSO4 minus, so all those things are there. Now let's come to the new question. Which of the following is a temporary effect? Hyperconjugation, electromeric, inductive effect or resonance effect? We all have dealt with this question. See, if we talk about hyperconjugation effect, so hyperconjugation effect, basically in my first lecture also, I have completely discussed it, the role of hyperconjugation for the stability of carbocation is there. Anushka is saying hyperconjugation with question mark. Don't worry, go back to the playlist, go back to the live session. There you will find, my first lecture will be there for chemistry. And on that day I have discussed hyperconjugation in detail, because explaining all these effect in one go is not, feasible. And you can even go back to the GOC Kataz organic paras. There is a playlist, and from there also you can learn this in detail. Here I will discuss only certain basic part which is essential to know this. Hyperconjugation, basically it has a stabilizing effect. It is permanent effect, and it involves the delocalization or the transfer of sigma bond in the form of pi bond in case of alkenes, free radicals and carbocation. Okay, so this one is permanent effect because completed. Now let's talk about electromeric effect. Electromeric effect, okay, it actually occurs only in the presence of reagent. Okay? And the type of electromagnetic effect observed completely depends on what kind of reagent is attacking the given organic compound. So this electromagnetic effect is basically, again, you can understand that is temporary effect. If certain effect has to be produced in presence of certain reagent, then definitely that is going to be the temporary effect. So electromagnetic effect is temporary. Again, inductive effect. So inductive effect is due to electronegativity difference. Either there is donation of electrons or withdrawal of electrons from the carbon bonds, and so that is called inductive effect. Again, the electronegativity is a permanent phenomena, so therefore inductive effect is also permanent phenomena. Okay. Now, if we talk about resonance effect, resonance, again, it is a stabilizing effect. You all have studied that it actually, what it does, it actually averages the various different properties that are found in a given molecule. Suppose carbon dioxide bond length are neither equal to the single C double bond O, or not equal to the C double bond O, single C double bond O. It is basically in between that. So it is because of the resonance effect which actually averages the property. And then different type of resonance are possible, plus R, minus R. You all have studied this. So this is also a permanent effect. So these three are basically permanent, and second one is the temporary effect. Is this clear to all of you? In detail I will explain some other time. So now let's proceed to the next question. That is, most stable carbanion is. Yes, Asim, very good. That it is electromagnetic effect which is temporary. Now, most stable carbanion, definitely we have to look at the charge here. Okay. So, if charge is more, so definitely the substance will be very reactive. Okay. Stability will be less. Okay, Nidhi? So we have to find out an organic compound or this group where lesser finally negative charge is there, or tendency to donate these negative charges less, because charge species, they are reactive. Okay. You all are also charged up for the NEET. So you are practicing lots of questions, and more NEET questions are being practiced by all of you, so that you can get charged up and perform better in examination. Yes. So here you can see that CH3 CH2 minus is there, CH3 CH minus is there, CH3 C minus is there. Now again we have to think about this. Here carbon is sp hybridized. This one is also sp hybridized. Okay. So because of this sp hybridization, what happens here is that tendency for the stability increases a lot, because someone is saying sir 4 ऐसा क्यों लगता है 4? Okay, I will discuss it, don't worry. रीजन बताइए फोर्थ का. चलिए. So tendency to donate these electrons, नहीं, that will not affect here. Stability minus I. 4 is carbocation, not carbanion. Exactly. यहाँ पे बहुत सारे बच्चे गलती ये कर रहे हैं कि they are either trying to apply hyperconjugation effect, but hyperconjugation will not be that much applicable here, because hyperconjugation, I have already told you, takes place in case of free radicals or carbocation. Hyperconjugation कहाँ है राहुल? It is negatively charged. या तो कार्बोकटायन पे लगता है या फ्री रेडिकल पे लगता है. कार्बोनायन पे तो हाइपर कंजुगेशन का इतना ज़्यादा इफेक्ट होता नहीं. ओके. सो यस विवेक त्रिपाठी. सो दैट्स वाई this CH is sp hybridized, and because of this hybridization what will happen? The electronegativity will be, of this high carbon will be more. And due to this, what will happen? Electronegativity of this carbon is more, so it can hold more number of more negative charge on itself. Tendency to donate electron becomes less, and therefore correct answer is option 3. Okay, not the 4th one. So I hope this solves your doubt. So these were the questions which we have discussed. Okay, so that's all for today. If you have any doubt, you can ask in the comment section. Thank you very much.